chapter. We will start chapter 3, which talks about mechanical properties of materials. In this chapter, we will learn different stress-strain relationships for in case of tensile tests, compression tests, in case of shear. Okay. Second, we will see properties of as hardness of a material, how to determine it, and we'll study the effect of temperature on the properties of a material. And finally, we will talk about fluid properties and viscoelastic behavior of polymers. Now, to start with, the mechanical properties are very important to determine the material's behavior when subjected to mechanical stresses. And these properties include elastic modulus, ductility, hardness, and many other measures of strength of the material. Now, we have a problem concerning the mechanical properties desired, because in general, mechanical properties desired for the designer are, for example, a high strength, but this can usually make manufacturing more difficult, because if you have a very hard material, then it will be difficult to undergo a deformation for the material. And you know that in any manufacturing process in general, the objective is to change the properties or to change the shape. And to do this, we need to undergo a certain deformation for the material. So this is why some mechanical properties can be we should do a compromise between what the designer needs and what the manufacturing processes require. Okay, so we will see that for different materials of different properties, we have different manufacturing processes. And some manufacturing processes are more suitable for metals with high strength, for example, than others. Okay, and in this course, we will see the different manufacturing processes and the different materials that are used in these processes. So now to start with, we will talk about stress-strain relationships. We have three types of static stresses to which materials can be subjected. We can have the tensile stresses, in which case the material is stretched. We can have the compressive case where the material is squeezed. And we have the shear type, causing adjacent portions of the material to slide against each other. And for all cases, we can draw what is called stress-strain curve, which is the basic relationship that will describe mechanical properties for all three types. And we will learn together how to determine properties of materials from this graph. Now, to start by the tensile test, it's a very common test for studying stress-strain relationships, especially for metals, and it consists on taking a specimen of a initial length L0. So here we can see the initial specimen, and we apply forces at the two ends of the specimen, causing it to stretch. Now, at any instant, we can measure for each force applied what is the corresponding length of the specimen, and we'll continue this until fracture. Okay, so in this test, a force will pull the material, elongating it and reducing its diameter. We can see in this figure the initial state, and in this figure, at any time with a certain elongation L, how will be our specimen. Now, what is the type of machines used to conduct this test? You have here, you can see it here. Okay, this is the tensile test setup. So what we will do is we put a specimen between crossheads. We have a fixed crosshead and a moving crosshead. So by moving the crosshead downward, this one, by moving it downward, we can cause elongation of the specimen. And the whole system is fixed to a table, which is related to a base and actuator, which is causing the displacement of the crosshead. Okay, so this is in summary the representation of the tensile testing machine. And we can see here that the tensile test specimen is marked with 2 points, which we call gauge marks. The gauge marks are used to measure the variation of length of the specimen. Okay, so this is the initial length, and as you are applying tension forces to the specimen, the distance here will increase between these 2 points. And we will measure it to see the variation of L with the force applied on the specimen. Okay. Now we will see what are the different phases in a figure for the specimen length. So here you have initially, at the initial state, the length is L0. So this is the case of no load applied on the specimen. Then the machine test will gradually increase the applied force. So we will have a gradual force variation. And under the effect of the force increase, the length of the specimen will also increase. Now for the first part, as you can see here, the elongation is uniform. This means that the cross-sectional area of the specimen remains constant. Okay, this is the case here. This is also the case here until reaching a certain stage where we will have no more uniform cross-sectional area. This is the starting of necking part. Okay, in the necking part, what will happen is we'll have formation of a certain geometry which is similar to the neck. Okay, and in this case, what will happen that instead of the whole specimen supporting the force F to undergo elongation, the whole deformation will take place now in a very limited zone, the necking part. So we will have a drastical decrease in this area, which will lead to rupture at the end. Okay, so here, whenever you see the formation, the reduction at a certain local part, not in the whole specimen, then necking will start. And if you continue to apply a force on the system, and we will see together that whenever necking starts, you don't need any more to increase your force F to continue the formation, because now it is much easier to continue the formation because you are acting locally on a small part. Okay, so you need a lower force to continue the formation until reaching a certain step where you have a rupture. Okay, and at the end, to determine the final length before rupture, what you do is you join back these two parts, you put them together, and you measure the final length, which will be used to calculate what is called the elongation of the specimen, which is L final minus L0 over L0. Okay, please stop me if you don't understand anything. Now,
دكتور, does knocking occur بالنص على القد ولا it can be anywhere?
هلا هي in general بتصير على النص, but yes, it can be anywhere. You know why? Because it depends. Sometimes you have a zone that is weaker than the other. Yani for a certain reason, you know that any material is not perfect. You might have a certain cross section that is little bit weaker than the others. This is why necking in general will take place in this in the region that is weak. Okay. If not, it will be at the middle. يعني in case you don't, you have complete symmetry, it might be at the middle. In this case. Okay. Now, we define two types of stresses: engineering stress and true stress. What is the difference between them? First, the engineering stress is defined as the force divided by the original area. Okay. Since we are dividing by the original area, which is a constant, A0, then the engineering stress, if you want variation, will represent the variation of the load applied, the force applied on the specimen. So it will not actually illustrate the variation of stress, but the variation of force. This is why we call it engineering stress, and we will define after what is called true stress. The true stress, on the other hand, is defined, so sometimes the symbol here will be sigma. This is a symbol of stress, sigma engineering. So sigma engineering is F over A0, while true sigma, true stress, okay, is equal to F over the actual area of the specimen at any time. Okay, so this is actually representing the stress, while here it is called engineering stress, and it's directly proportional to the applied force. Okay, so first we will try to define the characteristics that we can identify from engineering stress curves. So let us see here. Just before this, in general, we plot the engineering stress function of the engineering strain. Okay, what is the engineering strain? By definition, the engineering strain represents the elongation, okay, which is L minus L0. So it's delta L over L0. So it's the percentage of elongation at any instant. This is the engineering strain, okay, where E represents the engineering strain, L is the length at any point during elongation, and L0 is the original gauge length. Now, in general, the symbol we use is epsilon. Okay, you are familiar, I think, if you have taken mechanics of materials. In general, the engineering strain is of symbol epsilon E. So epsilon engineering. Okay. Now, if we want to plot the engineering stress versus the engineering strain, we obtain the stress strain plot, engineering stress strain plot. Okay, and this is a very important plot from which we can get a high number of characteristics of the materials. First, an important characteristic is the yield strength that we will define together. So this is the yield strength. We can define also the tensile strength, which is corresponds to the maximum load applied, and we can define two phases, main phases, which are the elastic region and the plastic region. So here, as you can see, if you look at your figure, you have first an elastic variation of sigma with epsilon. Okay, this is called the elastic region, characterized by a linear profile, and the linear profile has a slope. The slope is what? Do you remember? Which property is given from the slope of the elastic region?
Modulus.
Yes, exactly. Very good. The modulus of elasticity. Okay, or Young modulus. Okay. So here in this region, in the elastic region, we can say that the equation of this curve can be given from sigma engineering is equal to the modulus of elasticity or Young modulus times epsilon engineering. Okay. Now, at a certain point, which is called the yield stress, when we reach the yield stress, what will happen is that you will have a transition from elastic to plastic region. And this transition is marked by the variation in slope. So here the slope is equal to the modulus of elasticity, while in the plastic region, as you can see, just until reaching the necking part, the slope will decrease. Okay, why the slope will decrease? Because here you can deform your material easily. When you go into the plastic region, the deformation becomes easier. This is why we will see that a lot of manufacturing processes rely on deformation in the plastic region, because it is easier to operate in the plastic region and cause deformation than in the elastic region. Okay, so until reaching, so here, as you can see, since it's easier to deform, the slope will decrease, and we will reach the maximum load. At the maximum load, we have the starting of the necking process. So the necking process will have decrease in engineering stress. Why? Because as we have seen together, the engineering stress is directly related to the load applied. It is F over A0. And once we start necking, we have seen that it will be much easier to deform. So even I don't need anymore to increase my force. My force will be, I can put lower forces to continue deformation. This is why after necking, the engineering stress will be reduced until the final point corresponding to the fracture. Okay? So now we will define together all these properties in the coming slides. So first, elastic region in stress strain curve. So the relationship between stress and strain is linear in this region. and is given by the Hooke's law in the form of sigma engineering equals to the modulus of elasticity E times epsilon, which is the engineering strain. The material in this case returns to its original length when stress is removed. So this is one of the main properties of elastic region, that if I remove the load acting on the specimen, it will go back to its initial state. Okay, and E represent a measure of the inherent stiffness of the material. So it's similar to, if you want, to the spring constant. If you have a spring, then the force in the spring is equal to K times delta L. K represents the stiffness of the spring. Here, E is the stiffness of the material, okay? Or it represents its elastic properties. And of course, E is variable for different materials. So now if we go back just to the graph, so to see what is the difference between removing load in elastic region or removing load in plastic region. If you have a specimen and you applied on it a certain stress, it will undergo a certain deformation. Let's say you applied a stress at this point. So you can read what will be the corresponding engineering strain. And if you remove the load, what will happen is that your specimen will go back to its initial state. Okay, so it will take some time, but at the end, it will go back to its initial state. Zero stress, zero strain. On the other hand, if you applied a higher force to your specimen and you reached the plastic region, okay, then you will not be able anymore to go back to the initial state. You will have a permanent deformation. And in general, to determine the permanent deformation, what we do is, from this point, we draw a parallel to the elastic region, and you will say that it will undergo a permanent deformation. And the permanent strain can be, you can read it from the graph here. Okay? Now, concerning the yield point, as we have talked together, as stress increases, a point in the linear relationship is finally reached when the material begins to yield. So the yield point is the transition from elastic to plastic region. So the yield point can be identified by the change in slope at the upper end of the linear region. And the yield point is a strength property. So higher is the yield point, higher is the strength of the material. Now, other names that can be given for yield points are yield strength, yield stress, and elastic limit. Now, a certain note about the yield strength. Sometimes the yield strength is very clear in the figure, and sometimes it's not. So if I go back to the figure, we will learn a technique to find the yield strength in case if it is not clear on the figure. So here, for example, the transition is clear. So here, nearly yield point is here when you have transition from linear to curve variation. Okay. However, sometimes you might have this profile, so it can be like this. You have a curve like this. So it will not be clear what is the limit between the elastic and plastic region. So we have a method called offset method, which consists on the following. It's a very simple method. We put epsilon, we take the point epsilon equal 0.2%, which corresponds to epsilon equal, so E equal to 0.002. Okay, and from this point, what you do is that you draw a parallel line to the elastic plot. This line will encounter the graph in one point, which is corresponding to the yield point. So as you can see here, this will give you a very close result to the yield. Okay, so by this method, if the graph is not very obvious where the transition is, using this method, you can find the actual value of the yield stress. Okay, any question on this? So let us continue. Now, the yield point marks the beginning of the plastic deformation, and the stress-strain relationship will no longer be guided by Hooke's law. And we will see together that we have another equation that will describe the plastic region. We will see it in this chapter. As the load is increased beyond the yield stress, elongation proceeds at a much faster rate than before, as we have seen together, because in the plastic region, it will become easier to deform the material. This is why the slope of stress versus strain will decrease. Okay, so this will cause the slope of the curve to change dramatically, and it will decrease. Now, tensile strength and stress strain curve. In general, the elongation, along with the elongation, we have a uniform reduction in cross-sectional area consistent with maintaining a constant volume. This will happen until we reach the maximum load. Okay, when we reach a maximum force, then we will start to have the necking process, in which case, okay, the area will not be reduced in a uniform way in the whole specimen, but we will have just area reduction in a small zone, which is the necking zone. Okay. Yes, Ralph. Okay, I will show again the offset method here. Just 1 minute, because one student is asking for this. I will repeat the offset method. So in the offset method, the idea is that sometimes the yield point is not very clear on the figure. Okay, the yield point represents the transition between the linear zone and the curved point, the elastic and plastic regions. Okay, so here, for example, it's clear that this point is the transition between the two. Sometimes the graph is not very clear, so you might have like this, for example, this variation. So here you cannot detect a punctual variation transition from elastic to plastic. This is why we come up with another method to find the yield points in case if it is not clear and on the figure, which consists on setting epsilon, which is the strain, equal to 0.2%. This is why it's called the 0.2% offset method. So we take epsilon E equal to 0.002, okay? And from this point, we draw the parallel line to the elastic region line. And this line will cross the curve at a certain point. Okay, this point corresponds to the yield strength. So as you can see here, we obtained the value, a very close value to the yield. Okay, so this is the offset method. Okay, welcome. Okay, so let us continue. Okay, so we were talking about how before necking, okay, as we increase the load, we have a reduction, uniform reduction of area. But at a certain state, when we reach the maximum force, okay, we have a force beyond which necking will start. So this will correspond to the maximum force that can be supported by the specimen before necking start, and it will correspond to the maximum engineering stress, because we have seen that the engineering stress is proportional to the applied force. And at this point, we have the tensile strength, also known as ultimate tensile strength. And it's defined as F maximum over A0. So if you get from the graph the tensile strength, which is the maximum, you can deduce what is the maximum load that can be applied on your specimen before starting necking. Now, another important property that can be measured from the graphs is the ductility. Okay, the ductility is the ability of a material to plastically strain without fracture. And if you want, the ductility is a qualitative property, and it can be represented by several quantitative properties. So one of the properties that can be a measure of ductility is the elongation. Okay, the final elongation, which is L final minus L0 over L0. And this represents the amount, the percentage of variation of length that the specimen can undergo before rupture. Okay, now another property that can also be a measure of ductility is in a tensile test is the area reduction. Okay, and the area reduction can be defined as follows: area reduction equals to, instead of doing the difference in lengths, now we do the difference in areas. But since the area is reduced, so we will put A0 minus A final, okay, over A0. These numbers will be different, okay, but both are a representation of the ductility, because the ductility represents the ability of the material to plastically strain without fracture. Okay, and as we said, we can talk about the ductility using several measures. One of them is the elongation, and the other them is the area reduction. Because here, higher is the percentages of elongation and area reduction, higher is the ductility of the material. Okay. Now, in case we are using the elongation measure, okay, then L final will represent the distance between gauge marks after the two pieces of specimen are put back together. So if you go back to the figure here, after rupture, just after rupture, you will have two parts. You will put them close to each other, and in this way you can measure the final length, which will allow you to calculate the elongation, which is L final minus L0 over L0. And if you want to use your graph to determine the ductility, if we go back to the engineering curve, in the engineering curve, the tensile strengths correspond to the maximum load. So to find the tensile strength, you just find the maximum point here, and it will correspond to the maximum stress, which is called tensile stress or tensile strength. And for the elongation, it can be calculated by finding epsilon final. Because what is the definition of epsilon final? It is the elongation, okay, which is a measure of ductility. Since epsilon final is equal to L final minus L0, okay, over, so this whole term over L0. So from here, you can measure the elongation using the graph, okay? Now, we move to the other type of curves we can draw in tensile test, with the which is the true stress versus the true strain. So first, we have seen that the engineering stress is not actually a measure of stress, but it's a measure of the force, because it's the force over a constant. If you want truly to find the variation of stress, we should divide the applied load by the actual area at any instant. So the stress value is obtained by dividing the instantaneous area into the applied load. Okay, so we get sigma equal F over A, where sigma is the true stress, F is the applied force, and A is the instantaneous area resisting to the load. Also, we define the true strain. Okay, what will be the definition of the true strain? You know that the engineering strain is L minus L0 over L0. So it's always referring back to the initial length. But if we want to be accurate, at each instant, we should refer to the current length. This is why if we want to define the true strain, okay, the total deformation delta L will be divided into small part dl. And dl will be, for each dl will be divided by the corresponding length of the specimen. So to find this true strain, we should do integration from L0 to L of dl over L. So the true strain will be given by ln of L over L0. Okay? Now we will see together what are the properties that we can get from the true stress strain curve. So as we have seen, the true stress strain curve will be different than the engineering curve. First, if you want to compare the true stress to the engineering stress, okay, let us go back to the definition. We have that sigma engineering is defined as F over, so it's F over A0, okay, while sigma true, okay, while sigma true is F over the actual area. So if I just do the ratio of these two, I will see that which one will be higher, the true engineering or the true stress or the engineering stress. Who will tell me which is higher in a tensile test? Very good. The true is higher. Why? Because if I do the ratio, okay, if I do the ratio, I obtain that sigma in true over sigma engineering is equal to A0 over A. Okay? And you know that in a tensile test, what will happen to the area in a tensile test? The area will be reduced. Okay? So in tensile test, I can say that this is smaller, this is higher than 1 in tensile test. Okay? While if I have a compressive test, it will be the opposite. Okay? So in tensile test, the true stress will be higher than the engineering stress. While in compression, if I take the absolute value of sigma, because you know that sigma in compression will be negative. But when I say sigma compression, so I take the positive value, okay? So sigma true compression will be smaller than sigma engineering compression. Because in compression, the area is increased of the specimen, while in tension the specimen area is decreased. Okay, so we will have opposite cases in tension and compression. In tension test, tensile test, sigma true is higher than sigma engineering, while in compression test, sigma true will be smaller than sigma engineering. Okay, now concerning the true strain and engineering strain, the true strain will be smaller than the engineering strain. Okay, because the first is, if you compare the two function L minus L0 over L0, which is equal to over L0, which will be equal to which will be equal to L over L0 minus 1, L over, so it is L over L0 minus 1. Okay, this is epsilon engineering. So if you compare it with epsilon true is equal to ln of L over L0. These two functions, if you compare them, you can see that in case of tensile strengths where L is higher than L0, you will have that epsilon engineering will be higher than, true strain engineering is higher than true strain. Okay, so by just comparing these two functions, you will see that the engineering strain will be higher than the true strain. Okay, and we will do problems on this. If you put the two graphs close to each other, you will see that the in tensile test, true stress is higher than engineering stress, while true strain is smaller than engineering strain. Okay, so now let us see what we can learn from this plot. First, we can also see an elastic region, and we will see together that in the elastic region, the true and engineering stress are very close to each other, and also the true and engineering strain are very close. So in this region, if you put the values, they will be you will not nearly see a difference in the two plots. Okay, because the values are very close to each other. This is why for the modulus of elasticity, you can, and by definition you get it from the engineering curve, but you can also find its value, a very close value, from the true stress plot. Okay, now also the yield point is defined in the same way. It is the transition between the elastic and plastic region. Okay, but the offset method is defined in the engineering curve. So if they tell you find the yield using the offset method, in general you use the engineering curve. But if you just have the true curve, it will not be you will not have a high difference if you use it on the true curve, because as we said, for both graphs, okay, in the elastic region, the points have nearly very close coordinates. And we will do this in examples, you will see this. Now, the difference between the graphs will begin in the plastic region. In the plastic region, you will have high differences between true and engineering curves, okay? And the true curve is sometimes much more helpful than the engineering curve to determine the start of necking. I will tell you why. Because in the engineering curve, you define start of necking at the maximum load. But in majority of cases, when they give you the engineering curve, the maximum will not be clear. You will have this, for example. If I give you this curve, you have a flat plate here nearly, and it's not easy to determine where is the maximum and where necking starts. This is why we go to the true stress strain curve, and we have a technique to determine the start of necking. How to do it? First, in the plastic region, we will see together that the curve can be given by equation k times epsilon to the power n. And we will learn together how to find these constants k and n, okay? So in this part, you can say I can define the equation as k times epsilon to the power n, okay? Now, this is called the flow curve, okay? If I draw it, if I consider that I don't have necking and I draw it for true strain after the necking zone, I will have what is called the flow curve. Now, how to determine the start of necking? I will compare the flow curve with the actual curve, okay? You will see that I have a separation point. Yani before necking, nearly the two curves will be the same. And after necking, there will be separation between the actual curve of plastic deformation and the flow curve. So the separation point is called the start of necking, and it will correspond to the ultimate stress. Okay, so here you can see that the start of necking can be identified from the separation of the two curves, and it will be in this way I can determine the start of necking from true stress, which was not clear in the engineering curve. Okay, so let us see. As you can see here, they name it projected curve if necking does not occur. Okay, and it's the name of this curve is called the flow curve. Okay, and I compare it with the actual curve to determine the separation point. Okay, so this zone, the zone directly after the yield point, is called strain hardening. Okay, so this part of the plastic region before necking, this is called the strain hardening zone. And the strain hardening zone, why we name it like this? Because you can see here that in order to increase the deformation, I need to increase the stress. So we call it strain hardening zone because I am able to reach higher stress in order to have higher deformation. On the other hand, this period will stop when we have start of necking, because when necking starts, the true stress will decrease. Okay, this is why before necking, the plastic region before necking is called strain hardening zone, and after necking, it is when the necking process starts, the true stress will be decreased, and we cannot say anymore that we are in the strain hardening zone. And the strain hardening zone is defined by the flow curve, which was observed to be of the form k times epsilon to the power n. Okay, I will open a new session to continue.